Hello and welcome to Infinite Science.
Tonight, we're going to take a journey together, not outward into the depths of space, but inward, deeper into our own galaxy than most of us have ever imagined going. There is something waiting there, at the very center of the Milky Way. Something ancient, something vast, something that has been hiding in plain sight for as long as stars have turned in the night sky. You can't see it with your eyes, you can't hear it, you can't feel it, but it's there. And tonight, we're going to find it together. So settle in, slow down, and let's begin this quiet descent into the heart of everything we call home.
When you look up at the night sky on a clear evening, far from the lights of the city, you might see a faint band of light stretching across the darkness. The ancient Greeks called it galaxies kyklos, the Milky Circle. We know it as the Milky Way, our home. A gentle river of starlight that has guided travelers, inspired poets, and sparked wonder in every generation of humans who have ever lived beneath it. It looks peaceful, doesn't it? Eternal and unchanging. A cosmic backdrop to our small lives, constant and reliable. The stars rise and set, the seasons turn. The galaxy drifts overhead like a cosmic clock, marking the passage of time with reassuring regularity.
But appearances, as we so often discover in science, can be profoundly deceiving. The calmness we perceive from our vantage point here on Earth is an illusion born of distance and scale. We are looking at the Milky Way from within, like a person standing in the middle of a vast forest, seeing only the trees nearby and assuming the entire forest is just as quiet and orderly. We see the stars closest to us. We see the familiar constellations. We see the gentle sweep of stellar light across the sky. And we feel safe, protected, comfortable in our corner of the cosmos. But what we don't see, what we can't see with our naked eyes, is what lies at the center of it all. Hidden deep within that river of light, buried beneath layers of dust and gas and the light of 100 billion stars, there is something else. Something that doesn't shine. Something that doesn't reveal itself easily. A presence so massive, so fundamentally strange, that it warps the very fabric of space and time around it. A sleeping giant. A silent shadow, a hidden heart that beats with a gravity so intense it defies our everyday understanding of reality.
The galaxy we call home is not as peaceful as it appears, and at its core, there is a darkness that holds everything together. Tonight, we will travel there. We will peer through the veils of dust and distance. We will follow the breadcrumb trail of evidence that astronomers have painstakingly assembled over decades, and we will discover what truly lies at the heart of the Milky Way. The journey begins now, with Earth beneath our feet and the stars overhead. And it ends 26,000 light-years away, in a place where the normal rules of physics break down, and reality itself becomes strange.
Let's begin our journey. Imagine for a moment that we could leave Earth behind, not just physically, but conceptually. Imagine we could shrink the distances, accelerate time, and travel inward toward the center of the Milky Way. We would need to cross an almost incomprehensible distance. Our solar system sits about 26,000 light-years from the galactic center. That means the light we see from that region tonight left its source 26,000 years ago, when humans on Earth were still hunter-gatherers painting animals on cave walls. When mammoths walked the frozen tundra and the Ice Age held much of the northern hemisphere in its grip. The photons that reach our telescopes tonight have been traveling through space for longer than human civilization has existed. But let's go there now. Let's move inward, collapsing that vast distance in our minds, seeing what lies between us and the galactic core. At first, the journey feels familiar. We pass neighboring stars, the ones we know by name. Proxima Centauri, just over 4 light-years away, the closest star to our Sun. Alpha Centauri, a triple star system visible from the southern hemisphere. Barnard's Star, a dim red dwarf that's been the subject of countless science fiction stories. These are our closest neighbors in the cosmic sense, though they're still trillions of miles away. Distances so vast that even traveling at the speed of light would take years to cross them. But we're not bound by such constraints in our imagination. We move onward, deeper into the galaxy. As we continue inward, the stars begin to grow more numerous. The space between them shrinks. We pass through the Orion Arm, the spiral structure where our Sun resides, a minor tendril of stars and gas extending outward from the galaxy's main body. The Orion Arm is just one of several spiral arms that wrap around the Milky Way, giving our galaxy its characteristic pinwheel shape. We move through it, watching the stellar density increase. What was once a sprinkling of isolated stars becomes a rich field. Thousands of stars per cubic light year, then tens of thousands. The night sky, if we could stop and look back toward Earth, would be brilliant beyond description. So many stars that they would cast shadows. So much light that true darkness would be impossible. Now we begin to encounter the great nebulae, vast clouds of gas and dust where new stars are being born. The Eagle Nebula, famous for its pillars of creation, captured in iconic images by the Hubble Space Telescope. The Carina Nebula, home to some of the most massive stars known, giants that burn through their fuel at prodigious rates and will explode as supernovae within a few million years. These stellar nurseries glow with the light of newborn suns, their radiation illuminating the gas around them in shades of red and blue and gold. We pass through them like a ship moving through fog, and on the other side, there are more stars, always more stars. They grow denser the deeper we go. The darkness between them becomes less dark. The combined light of billions of distant suns creates a perpetual twilight, a cosmic glow that never fades.
We pass star clusters now, ancient collections of stars that formed together billions of years ago and have remained bound by gravity ever since. Globular clusters, spherical swarms containing hundreds of thousands of stars packed into a region just a few dozen light years across. They move through the galaxy like schools of luminous fish, orbiting the galactic center in great elliptical paths that take hundreds of millions of years to complete. Some of these clusters are older than almost anything else in the galaxy. They were here when the Milky Way was young, when the first generations of stars were just beginning to enrich the interstellar medium with heavy elements.
They've witnessed billions of years of galactic history, and they will witness billions more.
As we move deeper, something begins to change. The stars are moving faster now, not just drifting through space at the sedate pace we're used to near Earth, but racing along their orbits at speeds that seem impossible. Their paths around the galactic center are tighter, more frantic. Gravity is growing stronger. We can feel it, in a sense, in the way the stellar orbits curve and accelerate. Something massive is ahead. Something with gravitational influence powerful enough to fling stars around like pebbles. We pass through thicker clouds of dust now. These clouds, made of tiny grains of carbon and silicon compounds, absorb visible light, hiding what lies beyond them. If we were traveling in an ordinary spaceship, using ordinary telescopes that see invisible wavelengths, we would be flying blind now. The galactic center would be completely obscured, hidden behind a curtain of dust so thick that even the brightest stars cannot penetrate it. This is why, for most of human history, we had no idea what lay at the galaxy's core. We simply couldn't see through the dust. But we can imagine peering through those veils, using other wavelengths of light. Infrared radiation, with its longer wavelength, can pass through dust more easily. Radio waves, even longer still, are barely affected by the dust at all. X-rays from hot gas can also penetrate the obscuring clouds. By using these different windows into the galactic center, astronomers have slowly built up a picture of what lies beyond the dust. And as we approach using these other eyes,
these other ways of seeing, we begin to sense something ahead. Not see it exactly, but sense it. A gravitational presence, a weight in the fabric of space. The stars around us are moving in strange patterns now, their orbits describing elaborate loops and curves around something we cannot yet identify. Some of these stars are moving at speeds that seem impossible. Hundreds of kilometers per second, thousands of kilometers per second. They whip around an invisible center like planets orbiting a sun, but faster, tighter, more desperate. Their motion speaks of immense gravity, of mass concentrated in a small region, of something pulling them with irresistible force.
What could cause stars, objects so massive they dwarf our entire solar system, to move like that? What force could be strong enough to accelerate these titanic spheres of plasma to such tremendous speeds? We're getting close now, close to the answer, close to the truth that has been hiding here for billions of years.
The stellar density is extraordinary here. Millions of stars packed into a region just a few light years across. So many stars that collisions, though still rare, actually happen occasionally. So much light that any planet in this region would experience perpetual day, illuminated by hundreds of nearby suns. The environment here is harsh. Radiation levels are high. The tidal forces from passing stars would strip planets from their orbits. This is not a place conducive to life as we know it. This is a place of extremes. And at the very center, at the gravitational heart of all this chaos and density and motion, we find it. Or rather, we find where it should be. There is nothing to see, no glowing object, no bright beacon marking the galactic center. Just darkness. But it's not an ordinary darkness. It's a darkness that pulls, a darkness with weight, a darkness that bends light itself so severely that nothing, not even light, can escape once it crosses a certain boundary. This is a black hole, and not just any black hole. This is a supermassive black hole, millions of times more massive than our Sun, sitting at the gravitational center of the entire Milky Way galaxy. Scientists have given it a name, Sagittarius A, or SGARA for short, pronounced Sagittarius A star. It resides in the constellation Sagittarius, as seen from Earth, hidden behind those vast curtains of interstellar dust we passed through moments ago. We have arrived. We have found the hidden heart of the galaxy, and now we must try to understand what we're looking at. But what is a black hole, really? The name itself can be misleading. It's not a hole in the conventional sense, not a tunnel or a void or an absence of something. It's quite the opposite. A black hole is an object of such extreme density, such concentrated mass, that it creates a gravitational field from which nothing can escape. Imagine taking the entire mass of a star, or in this case, millions of stars.
Think of it this way. When you throw a ball up into the air on Earth, gravity pulls it back down. To escape Earth's gravity entirely, to fly off into space and never return, that ball would need to be thrown at about 11 kilometers per second. That's Earth's escape velocity. For the Sun, with its much stronger gravity, the escape velocity is over 600 kilometers per second. But for a black hole, the escape velocity at a certain distance, a boundary we call the event horizon, is faster than light itself. And since nothing in the universe can move faster than light, nothing that crosses that boundary can ever come back. Not matter, not energy, not information, not even time itself behaves normally there. It's a one-way door in the fabric of reality, a point of no return, a cosmic trap from which there is no escape. The event horizon is not a physical surface. There's no wall there, no barrier you could touch. It's simply the mathematical boundary where escape becomes impossible. Cross that line, and you're lost to the external universe forever. You could fire your rocket engines at maximum thrust. You could try to climb back out, but you would fail. The very geometry of spacetime has become so warped that all paths lead inward. There is no out anymore. There is only deeper in, toward the singularity at the center. And yet, for all its power, for all its strangeness, this object does not announce itself. It does not glow. It does not radiate light. It simply exists, a presence defined not by what it emits, but by what it prevents from escaping. It is, in the most literal sense, invisible. We cannot see it directly. We can only infer its existence from the effect it has on everything around it. The stars that orbit it, the gas that heats up as it spirals inward, the light from background objects that gets bent and distorted as it passes nearby. These are the signatures of the black hole. These are the ways it reveals itself without actually being visible.
And that effect is profound. The black hole's gravity reaches out across the entire inner galaxy, organizing stars into their orbits, shaping the distribution of gas and dust, determining the structure and dynamics of the galactic center. It is, in a very real sense, the anchor point of the Milky Way, the hub around which everything else revolves. Remove it, and the galaxy would be fundamentally different. Perhaps it wouldn't exist at all in its current form. Perhaps the stars would fly apart, no longer bound by sufficient gravity. Perhaps structure and organization would dissolve into chaos.
But the black hole is there. It has been there for billions of years, and it will remain there for billions more, long after the last stars have burned out and the universe has grown cold and dark. Black holes are among the most enduring objects in existence. They are, in a sense, the final state of matter, the ultimate endpoint of gravitational collapse. Once formed, they persist essentially forever, slowly evaporating through quantum effects, but on timescales so long, they make the current age of the universe look like an eye blink. Sagittarius A is 4 million times more massive than the Sun. 4 million solar masses of pure gravitational potential compressed into a region about 44 million kilometers across. That's the diameter of the event horizon, the boundary of no return. It sounds large, and by human standards, it is enormous. But in cosmic terms, it's remarkably compact. You could fit the entire black hole inside the orbit of Mercury, the innermost planet of our solar system. The Sun itself has a diameter of about 1.4 million kilometers, making the event horizon only about 30 times wider. And yet this region contains 4 million times as much mass. This is the paradox of black holes. Immense power contained in a relatively small space. Infinite density concentrated at a point so small we call it a singularity, where our current understanding of physics breaks down completely. At the singularity, general relativity predicts that density becomes infinite, that space-time curves infinitely, that the normal laws of physics cease to apply. We don't know what really happens there. We suspect that quantum effects, not included in general relativity, become important, that a full theory of quantum gravity would be needed to properly describe the singularity. But we don't have that theory yet. The singularity remains a mystery, a place where our knowledge ends.
But we don't need to understand the singularity to understand the black hole's effect on the galaxy. The event horizon, the boundary we can calculate and observe, is enough. And it's clear that Sagittarius A dominates the gravitational landscape of the galactic center. Every star within several light years is affected by its gravity. Many are in orbit around it, following elliptical paths that bring them perilously close to the event horizon before swinging back out into safer regions. These stars are witnesses to the black hole's existence, proof that something massive and invisible sits at the exact center of the Milky Way.
Let's talk about scale for a moment, because scale is everything when trying to truly grasp what Sagittarius A represents. Numbers alone won't do it justice. Our minds aren't built to comprehend the kinds of magnitudes we encounter in astronomy. But we can try. We can use comparisons and analogies to bring these vast quantities down to something more relatable. Sagittarius A has a mass approximately 4 million times that of our Sun. Let that sink in for a moment. The Sun is already enormous by human standards. It contains about 330,000 times the mass of Earth. You could fit over 1 million Earths inside the Sun's volume. The Sun's gravity keeps our entire solar system organized, holding 8 planets, dozens of moons, countless asteroids and comets, all in stable orbits. It's the dominant gravitational force in our local cosmic neighborhood. And yet, the black hole at the center of our galaxy is 4 million times more massive than that.
If you could somehow place Sagittarius A where our Sun currently sits, its event horizon would extend to about 17 times the distance from the Sun to Earth. The innermost planets would simply vanish beyond that boundary, falling into the darkness, gone forever from our universe. Mercury would be swallowed, Venus would be swallowed, Earth would be swallowed. Mars might survive, orbiting just outside the event horizon, but the tidal forces would be immense. The side of Mars facing the black hole would experience significantly stronger gravity than the far side. These tidal forces would stretch the planet, potentially tearing it apart over time.
This is called spaghettification, and it's what happens to anything that gets too close to a black hole. The difference in gravitational pull between near and far sides becomes so extreme that objects are stretched into long, thin shapes before being torn apart completely.
But Earth is safe. We're 26,000 light-years away. At that distance, the black hole's gravity is negligible. We don't orbit Sagittarius A directly in any meaningful sense. Instead, we orbit the collective gravitational center of the entire inner galaxy, which happens to coincide with the black hole's location. The black hole contributes to that total gravitational field, certainly, but so do millions of stars and vast quantities of dark matter. We're held in orbit by the combined gravity of everything interior to our position, not by the black hole alone.
Still, the black hole's influence is important. It helps organize the galaxy's structure. It affects the motion of stars in the inner regions. It shapes the distribution of gas and dust. And it serves as a marker, a reference point. The galactic center is defined by the location of Sagittarius A. When astronomers talk about the center of the Milky Way, this is what they mean. Not just a general region, but a specific location marked by a specific object. The supermassive black hole is the hub of our galaxy. And here's what makes it even more remarkable. This object, this concentration of mass and gravity, exerts its influence across hundreds of light-years, despite occupying a space that, while large, is minuscule compared to the galaxy as a whole. The Milky Way is about 100,000 light-years in diameter. The black hole's event horizon is about 16 light-minutes across. That's the distance light travels in 16 minutes. For comparison, light takes 8 minutes to travel from the Sun to Earth. So the event horizon of Sagittarius A is roughly twice the Sun-Earth distance in diameter.
Put another way, if the Milky Way were the size of North America, Sagittarius A would be smaller than a single bacterium. And yet that bacterium-sized object, in this analogy, contains 4 million times the mass of our Sun. It's a concentration of matter so extreme it defies everyday intuition. We have nothing in our normal experience to compare it to. The densest materials we encounter in daily life, things like lead or gold, have densities measured in grams per cubic centimeter. The density inside a black hole's event horizon exceeds that by factors so large they require scientific notation to express. And at the singularity, assuming it truly exists as general relativity predicts, the density becomes infinite.
All the mass compressed into a point with zero volume. Infinity divided by zero. Mathematics breaking down. Physics reaching its limits. This is what sits at the heart of our galaxy. An object that challenges our understanding of reality itself. An extreme of nature so profound that it forces us to confront the fundamental strangeness of the universe we inhabit. How do you find something that cannot be seen? How do you prove the existence of an object that emits no light, reflects no radiation, and hides behind clouds of dust so thick that even the brightest stars in the galactic center are rendered invisible to optical telescopes. This was the challenge facing astronomers in the 20th century. They suspected something unusual existed at the galactic center. Hints had been accumulating for decades. Radio emissions suggested energetic processes. The structure of the galaxy implied a massive central object. Theoretical work on black holes, beginning with Einstein's general relativity and continuing through the work of physicists like Carl Schwarzschild, Subramanian Chandrasekhar, Robert Oppenheimer, and Stephen Hawking, suggested that such objects could exist. But suspicion is not proof. Theoretical possibility is not observational confirmation. To truly know that a supermassive black hole existed at the center of the Milky Way, astronomers needed evidence, direct, undeniable, quantitative evidence.
The answer came not from looking at the black hole itself, but from observing what happened around it, from watching how nearby stars moved, from mapping their orbits over many years and asking the question, what could make them move like that? What central mass would be necessary to produce the observed orbital velocities and periods?
This work began in earnest in the 1990s, though the groundwork was laid decades earlier. Two teams of astronomers, working independently but with similar goals and methods, embarked on a patient, meticulous campaign to track individual stars in the region surrounding the galactic center. One team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at the University of California, Los Angeles. Both teams used some of the most powerful telescopes on Earth. Genzel's team primarily used the Very Large Telescope in Chile. Gez's team used the Keck Observatory in Hawaii.
These telescopes were equipped with adaptive optics systems, sophisticated technology that could compensate for the blurring effects of Earth's atmosphere by measuring atmospheric distortions in real time and adjusting the telescope's mirrors to counteract them. This allowed the telescopes to achieve much sharper images, approaching the theoretical limits of their resolution.
They also observed in infrared wavelengths, which could penetrate the dust that obscures the galactic center in visible light, and they watched, year after year, patiently recording the positions of stars, noting their movements, building up a picture of the gravitational landscape at the heart of the galaxy. This was not quick work. It was not glamorous work. It required dedication, persistence, and faith that the long-term investment would pay off.
And slowly, over the course of years and then decades, a picture began to emerge. The stars near the galactic center weren't just moving quickly, they were moving impossibly quickly by the standards of stars elsewhere in the galaxy. Some of them had velocities exceeding 5,000 kilometers per second. That's more than 1% of the speed of light. These are speeds we associate with cosmic ray particles, not with stars. And yet there they were, moving at these tremendous velocities. And they weren't flying off into space. They were in orbit, bound by gravity, circling around a common center. A center where there was nothing visible, no bright star, no cluster of stars, just radio emissions and a compact infrared source, and, most tellingly, this wild collection of stars whipping around at impossible speeds. One star in particular became famous. It's been designated S2 or sometimes S02, depending on which research team's nomenclature you use. This star follows an elliptical orbit that brings it extremely close to Sagittarius A. At its nearest approach, its periastron, it passes within about 17 light hours of the black hole. That might sound like a large distance, but in cosmic terms, it's nothing. It's closer than Neptune is to our Sun. And S2 completes this entire orbit in only 16 years. Our Sun takes 230 million years to orbit the galactic center. S2 does it in 16 years. The difference is distance and mass. S2 is so close to the central object that it feels an immensely stronger gravitational pull. And that pull accelerates it to tremendous speeds. At its closest approach, S2 is moving at nearly 3% of the speed of light, about 8,000 kilometers per second. By carefully measuring S2's orbit and the orbits of many other stars in the region,
astronomers were able to calculate the mass of the invisible object they were orbiting. The mathematics are based on Kepler's laws, the same laws that govern the motion of planets around the Sun. These laws, formulated by Johannes Kepler in the early 17th century based on observations of Mars, relate the size and period of an orbit to the mass of the central object. When you know how large an orbit is and how long it takes to complete, you can work backward to determine how much mass must be at the center to produce that orbit. It's straightforward physics, elegant in its simplicity.
And the numbers kept coming back the same. 4 million solar masses, give or take a few percent, depending on which stars you looked at and how precise your measurements were, but always in that ballpark. 4 million times the mass of the Sun, all concentrated in a region smaller than the solar system. There was no escaping the conclusion. This had to be a black hole.
There was no other explanation that fit the data. No cluster of dark stars could be that compact without collapsing into a black hole. No collection of stellar remnants, neutron stars or white dwarfs, could occupy such a small volume. They would collide, coalesce, and form a black hole anyway. No exotic alternative, like a ball of dark matter or a wormhole or any other speculative object, fit the observations as well as a simple, straightforward, supermassive black hole. The evidence was indirect, yes. We weren't seeing the black hole itself, but it was overwhelming, undeniable, definitive. In the year 2020, Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics for this discovery. The Nobel Committee recognized their work as providing the most convincing evidence for the existence of a supermassive black hole at the center of our galaxy. It was a triumph of patient observation, careful analysis, and collaborative scientific effort. A reminder that some questions take decades to answer, that some truths reveal themselves slowly, only to those willing to watch and wait and analyze and think deeply about what they're seeing. The invisible had been made known. The hidden giant had been found. Sagittarius A was real. And now, all of humanity could know that our galaxy, this peaceful river of light we see in the night sky, has a massive black hole at its heart. But here's something curious, something that makes Sagittarius A even more mysterious and interesting than you might expect. For all its power, for all its immense mass and gravitational dominance, this black hole is remarkably quiet. It's not actively feeding, it's not devouring stars. It's not surrounded by brilliant accretion disks of superheated matter spiraling inward at relativistic speeds. It's just sitting there, dormant, silent, like a sleeping dragon on a bed of gold, surrounded by riches but uninterested in consuming them. This is unusual. When we look at other galaxies, especially distant ones, where we're seeing them as they were billions of years ago, we often see supermassive black holes that are anything but quiet. These objects, called active galactic nuclei, or AGN, are among the brightest objects in the entire universe. They're surrounded by accretion disks, massive structures of gas and dust that spiral inward toward the event horizon. As this material falls inward, gravitational potential energy is converted into heat through friction and compression. The gas gets hot, very hot, hot enough to emit X-rays, hot enough to create jets of matter and energy that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for thousands or even millions of light years, pumping enormous amounts of energy into the surrounding space, creating giant lobes of radio emission visible across cosmic distances. Some active galactic nuclei are so bright they outshine the entire rest of their galaxy combined. All that light, all that energy coming from a region no larger than our solar system. It's one of the most energetic phenomena in the universe, and it's all powered by matter falling into a supermassive black hole. The efficiency is remarkable. When matter falls into a black hole, up to 40% of its mass can be converted into energy through the process of accretion. That's far more efficient than nuclear fusion in stars, which converts less than 1% of mass into energy. Black holes, when they're actively feeding, are the most efficient power sources in the cosmos. But Sagittarius A is nothing like that.
It does occasionally flicker. There are brief, irregular flares of X-ray and infrared radiation that suggest small amounts of matter are falling into it from time to time. Perhaps a stray asteroid from the chaotic environment near the galactic center, perhaps tendrils of gas from a nearby molecular cloud, perhaps small fragments torn from stars that pass too close. But these events are minor, they're brief. They don't represent sustained feeding. They're more like snacks than meals.
For the most part, Sagittarius A is starving. It sits at the gravitational center of 100 billion stars, surrounded by vast amounts of gas and dust, and yet it consumes almost nothing. The accretion rate, the rate at which matter falls past the event horizon, is incredibly low. Current estimates suggest the black hole is accreting less than 1,000th of a solar mass per million years. That's almost nothing. At that rate, it would take trillions of years to double in mass.
Why? Why is our galaxy's black hole so quiet when others are so violent? The answer likely has to do with its environment and the history of the Milky Way. The region immediately surrounding Sagittarius A is relatively empty. Most of the gas and dust in the galactic center is in stable orbits, not falling directly inward. There isn't a steady supply of material to feed the black hole. Without fuel, without matter constantly falling past the event horizon, there's no accretion disk, no heating, no radiation, no jets. The black hole simply sits there, exerting its gravitational influence, but otherwise remaining dormant.
This hasn't always been the case. Evidence suggests that Sagittarius A was more active in the past. Observations of gas clouds in the galactic center show structures that could have been created by outflows from the black hole millions of years ago. There are hints of past activity in the distribution of stars and gas. It's possible that the Milky Way, like many galaxies, goes through cycles. Periods of activity when gas flows inward and feeds the black hole, followed by longer periods of quiescence when the fuel runs out and the black hole goes dormant.
We happen to live during a quiet period, and in a sense, we're fortunate. If Sagittarius A were actively feeding, if it were a quasar like the ones we see in distant galaxies, the galactic center would be a much more hostile place. The radiation would be intense. The jets, if pointed in our direction, could scour the galactic disk. Star formation in the inner galaxy might be disrupted or prevented entirely. The environment might be incompatible with the kind of stable, long-lived stellar populations we observe.
But instead, we have a sleeping giant, a black hole that is present, powerful, and essential to the structure of our galaxy, but which has chosen, metaphorically speaking, to remain quiet. It's there. It holds everything together, but it doesn't make a fuss about it. It doesn't demand attention. It simply exists, a silent presence at the heart of the Milky Way.
The question, of course, is whether it will always stay that way, or whether something might wake it up. What would happen if Sagittarius A woke up, if it suddenly began to feed? If something massive, perhaps a dense molecular cloud, or a wayward star, or even another black hole, fell into its gravitational well and began spiraling inward, providing fuel for a period of activity? It's a fascinating question to consider, though we should be clear from the start that this is not an immediate threat. There's no evidence that such an event is about to occur. But it's worth thinking through, both for what it tells us about black hole physics and for what it reveals about our galaxy's past and future.
First, let's be precise about what we mean by waking up. Black holes don't have consciousness. They don't sleep in any biological sense. They don't make decisions. They're not alive. They're simply concentrations of mass that follow the laws of physics. When we talk about an active black hole versus a dormant one, we're talking about whether the black hole has a supply of matter falling into it. The black hole itself doesn't change. It's the environment around it that becomes dramatically different. If Sagittarius A began accreting matter in significant quantities, the first thing that would happen is the formation of an accretion disk. Material falling toward the black hole wouldn't fall straight in. It would have some angular momentum,
some sideways motion, and this would cause it to spiral inward rather than plunging directly toward the event horizon. As the material spirals, it forms a disk, a flattened structure rotating around the black hole, and as the material in the disk rubs against itself, as particles collide and interact, friction generates heat, tremendous amounts of heat. The inner regions of the disk, closest to the black hole, where the orbital velocities are highest, would heat up to temperatures of millions of degrees, hot enough to emit X-rays. These X-rays would flood the inner galaxy. They would ionize surrounding gas clouds, causing them to glow. They would heat dust, causing it to emit infrared radiation. The galactic center, currently dark and invisible in optical wavelengths, would become brilliant. It would be one of the brightest objects in the sky, outshining many stars despite being 26,000 light-years away. And depending on the rate of accretion, depending on how much matter was falling in and how quickly, jets might form. These jets are one of the most spectacular phenomena associated with active black holes. They're narrow beams of matter and energy that shoot out from the poles of the black hole at close to the speed of light. The exact mechanism that produces them is still debated, but it involves the interaction of the accretion disk with powerful magnetic fields. Somehow, some fraction of the infalling matter gets redirected, channeled along magnetic field lines, and accelerated to relativistic speeds. The jets shoot outward perpendicular to the accretion disk, creating brilliant beams that can extend for thousands of light-years or more. If Sagittarius A formed such jets, and if they happened to be pointed in our direction or toward other populated regions of the galaxy, the effects could be significant. High-energy radiation from the jets would bathe nearby star systems. It might affect planetary atmospheres. It could potentially damage ozone layers, increase radiation levels on planetary surfaces, and make conditions more hostile for life. But we need to keep this in perspective. We are 26,000 light-years away from the galactic center. That's an enormous distance. Even if Sagittarius A became as active as the most violent quasars in the early universe, we would not be in immediate danger. The radiation would spread out as it traveled, weakening with distance according to the inverse square law. By the time it reached our corner of the galaxy, it would be intense, yes, but not civilization-ending, not planet-sterilizing. There would be effects, certainly. Increased radiation might affect Earth's atmosphere over long timescales. It could potentially increase mutation rates in surface organisms. It could disrupt satellite operations and affect radio communications. These effects would develop over timescales of thousands or tens of thousands of years, not overnight, not in a single catastrophic event. We would have warning. We would see the galactic center brighten. We would detect the increased radiation with our instruments long before it became dangerous. And realistically, the chances of Sagittarius A suddenly becoming highly active are extremely low. There would need to be a significant change in the galactic environment. A massive molecular cloud would need to be disrupted and fall toward the center. A star would need to pass too close and be torn apart by tidal forces, with the debris falling into the black hole. Another galaxy with its own supermassive black hole would need to merge with the Milky Way, causing massive disruption and funneling gas toward both galactic centers. These events are rare on human timescales. They happen occasionally over the billions of years of galactic history, but they're not imminent. They're not something we need to worry about in the next million years, or even the next 100 million years. So, when we talk about the black hole waking up, we're not talking about an immediate threat. We're talking about a possibility. A reminder that the galaxy is not static, that the forces at its heart are powerful and, under the right circumstances, could become active again. But for now, and for the foreseeable future, the giant sleeps, and we go about our lives in a galaxy held together by its gravity, largely unaware on a day-to-day basis that such a thing even exists. The sleeping giant is not a danger, it's a guardian, a stabilizing force, a gravitational anchor that has maintained the structure of our galaxy for billions of years and will continue to do so for billions more. We should not fear it. We should marvel at it. appreciate it, understand it as a fundamental part of our cosmic home.
Why does this matter? Why should we care about a black hole 26,000 light-years away, one that poses no immediate threat and which we cannot even see directly? Why dedicate telescopes and careers and decades of effort to studying something so remote and so invisible?
Because it's part of the story of where we come from. The Milky Way galaxy is not just our cosmic address, it's our origin. Every atom in your body was forged in the heart of a star or in the explosion of a supernova somewhere in this galaxy. The iron in your blood, the calcium in your bones, the carbon in your DNA, the oxygen you're breathing right now, all of it was created by stellar processes and scattered into space when those stars died. That material eventually coalesced into new stars, new planets, and eventually into us. We are literally made of stardust, made of the galaxy, made of elements that were synthesized in stellar furnaces and distributed through space by stellar death. And the galaxy itself, the structure that made all of this possible, exists in its current form in part because of the supermassive black hole at its center. Sagittarius A didn't create the galaxy, not exactly. The relationship between galaxies and their central black holes is complex, a kind of cosmic symbiosis that we're only beginning to understand. But what is clear is that galaxies and supermassive black holes grow together. They influence each other. They co-evolve. The black hole's gravity helps organize the stars into the spiral structure we observe. It affects the flow of gas in the inner galaxy. It may regulate star formation through feedback processes we don't fully understand yet. The galaxy, in turn, feeds the black hole, though in our case, only sparingly.
Understanding Sagittarius A helps us understand the Milky Way, and understanding the Milky Way helps us understand our own cosmic story. We are not separate from the galaxy. We are part of it, products of its evolution, children of its stars, beneficiaries of billions of years of stellar nucleosynthesis and galactic organization. And the black hole at its center, invisible though it may be, is part of that heritage, part of the chain of causation that led to us, part of the reason the galaxy has the structure it does, which in turn is part of the reason we exist.
There's also a deeper lesson here about the nature of reality itself. Sagittarius A reminds us that the most important things are often invisible. Gravity, the force that shapes the universe, cannot be seen. We see its effects, but not the force itself. We see planets orbiting, galaxies rotating, but we don't see the gravitational field that causes these motions. Dark matter, which makes up most of the mass of the galaxy and plays a crucial role in its structure and evolution, remains undetected except through its gravitational influence. We know it's there because we can see what it does, but we've never directly observed a dark matter particle.
Even the black hole, perhaps the most extreme object in the cosmos, reveals itself only indirectly, through the motion of nearby stars, through the faint glow of gas heated by friction as it spirals inward, through the shadow it casts against background light.
We live in a universe where the unseen often matters more than the seen, where the quiet forces are often the most powerful, where truth is not always obvious, and where understanding requires patience, careful observation, and a willingness to infer what cannot be directly perceived. This is a profound insight about the nature of reality. It suggests that surface appearances are often misleading, that to understand the world, we must look deeper, we must measure, we must calculate, we must think.
In a way, the search for Sagittarius A is a metaphor for the scientific endeavor itself. We cannot always see the truth directly, but we can observe its effects. We can gather evidence. We can build models. We can make predictions and test them against observation. And slowly, piece by piece, inference by inference, we can build up a picture of reality that is accurate even if it's not based on direct observation. We can know things we cannot see. We can understand things we cannot touch.
we can grasp truths that are hidden from our senses but revealed by our instruments and our mathematics. And there's something profoundly humbling about that, about knowing that we live in a galaxy held together by an object we cannot see, that the very structure of our cosmic home depends on a darkness at its heart. It puts our existence in perspective. We are small, fragile, temporary. Our individual lives last less than a century. Our species has existed for only a few 100,000 years. Our civilization, our technology, our science, all of it is less than 10,000 years old. We are newcomers to a galaxy that has existed for more than 13 billion years.
And yet, despite our smallness, despite our brevity, we have managed to understand something fundamental about that galaxy. We have discovered its hidden heart. We have measured the invisible giant. We have proven that a supermassive black hole, an object that would have seemed like pure fantasy to our ancestors, is real and sits at the center of our cosmic home. That's remarkable. That's powerful. That's cause for both humility and pride. Humility because it reminds us how small we are in the cosmic scheme. Pride because it demonstrates what we're capable of when we turn our curiosity and intelligence toward understanding the universe.
We are part of a galaxy that dances around an invisible center. And knowing that, understanding that, changes how we see the night sky, changes how we see ourselves, changes our sense of place in the cosmos. We are not just inhabitants of Earth. We are residents of the Milky Way, citizens of a spiral galaxy with a supermassive black hole at its heart. And that's a profound and wonderful thing to know.
Let's take a moment to reflect on the nature of invisibility itself. There's something almost philosophical about a supermassive black hole. It is, by definition, a thing that cannot be seen. Light cannot escape from it, and yet it exists. It has mass. It has influence. It shapes the galaxy around it. In some ways, it is the most important object in the Milky Way, the gravitational anchor point around which everything else revolves. And yet, it is defined by absence, by darkness, by what it doesn't emit, by what it prevents from escaping.
This creates an interesting parallel with other aspects of existence. How much of what's important in life is invisible? Love is invisible. You can see its effects, its expressions, but not the emotion itself. Thought is invisible. Consciousness is invisible. The things that make us human, that define our inner experience, cannot be directly observed by others. They can only be inferred from behavior, from speech, from action. And yet, they're real. They matter. They shape our lives as surely as gravity shapes the galaxy. Perhaps reality is structured in layers, a visible layer that we can perceive directly with our senses, and beneath that, layers of invisible forces and influences that determine how the visible layer behaves. Gravity holding the universe together, electromagnetic forces binding atoms into molecules, nuclear forces holding atomic nuclei together, quantum fields underlying all of reality. These are the foundations, the substrate, the hidden machinery that makes everything else possible. And we cannot see any of them directly. We can only see their effects.
Black holes are perhaps the ultimate expression of this principle. They are invisible by nature, not by accident. Not because they're far away or obscured by dust, though Sagittarius A happens to be both of those things as well, but because their gravity is so intense that light itself cannot escape. They are absence made manifest, darkness given form, a presence defined by what it excludes rather than what it includes. And yet this invisible object is crucial, essential. Remove it, and the galaxy would be different. The structure would change, the dynamics would shift. Stars would follow different orbits. The distribution of matter would evolve differently. The Milky Way as we know it depends on this invisible presence at its center. There's a lesson here about judging by appearances,
about the danger of assuming that what we see is all there is. The galaxy looks peaceful and ordered from Earth. The night sky appears constant and eternal. But beneath that appearance, there are forces and structures we never suspected until we developed the tools to detect them. The universe is deeper than it looks, more complex, more strange. And the more we learn, the more we realize how much we're missing when we rely only on our eyes. Sagittarius A is a reminder of that. A reminder to look deeper, to question assumptions, to use instruments and mathematics to reveal what our senses cannot detect, to build up understanding through inference and calculation and patient observation. This is the power of science. Not to make the invisible visible, necessarily, but to make it knowable, to bring it within the reach of human understanding, even if it remains beyond the reach of human perception.
And there's beauty in that. Beauty in the fact that we can know things we cannot see. Beauty in the mathematical elegance of general relativity, which predicts the existence of black holes as a natural consequence of its equations. Beauty in the patient work of astronomers tracking stars year after year, building up the evidence, proving the invisible giant's existence. Beauty in the collective human effort to understand the cosmos, to push back the boundaries of ignorance, to light up the darkness with the lamp of knowledge.
Sagittarius A exists in physical darkness, but our understanding of it represents a kind of light, the light of knowledge, the light of comprehension. We have illuminated something that cannot itself be illuminated. We have made known something that remains fundamentally unknowable in its interior, but can be characterized and understood in its effects. That's the triumph. Not seeing the black hole, but knowing it. Not observing it directly, but understanding it completely enough to make predictions, to test theories, to use it as a laboratory for exploring the most extreme physics in nature. The invisible can be known. The hidden can be found. The darkness can be mapped. That's what Sagittarius A teaches us. And it's a lesson that extends far beyond astronomy. In every field of human endeavor, there are hidden factors, invisible influences, forces that shape outcomes without being directly observable. And the methodology of science, the careful gathering of evidence, the testing of hypotheses, the patient building of understanding, can reveal these hidden factors, can make them part of our knowledge, can transform mystery into understanding. That's why studying Sagittarius A matters, not just for what it tells us about black holes or galaxies or gravity, but for what it demonstrates about the power of human curiosity and intelligence to understand even the most hidden aspects of reality. There's another layer to this story that's worth considering. The relationship between us and Sagittarius A is not just spatial, but temporal. The light we detect from the galactic center, the infrared and radio waves that carry information about the stars and gas clouds in that region, left that location 26,000 years ago. When we observe the galactic center, we're looking back in time. We're seeing the black hole as it was in the deep past, long before human civilization existed, before agriculture, before cities, before writing, before most of what we think of as human history. This is true for everything we observe in astronomy, of course. The farther away something is, the farther back in time we're seeing it. Light travels at a finite speed, so distance and time become linked. The sun we see in the sky is 8 minutes in the past. The nearest stars are years in the past. Distant galaxies are millions or billions of years in the past. When we look at the most distant objects observable, we're seeing the universe as it was shortly after the Big Bang, when it was young and hot and very different from today. But there's something particularly poignant about this when it comes to Sagittarius A. The black hole we study, the object we've spent decades learning about, exists in our deep past. The stars orbiting around it, the ones whose motions proved its existence, were in completely different positions when the light we're now seeing left that region. S2, the star that orbits so close to the black hole, has completed more than 1,600 orbits in the time it took for its light to reach us.
1,600 complete revolutions around the black hole, and we're only now seeing light from the first one.
And by the same token, we exist in Sagittarius A's future. If there were observers near the galactic center, somehow able to look at our region of space, they would see the solar system as it was 26,000 years ago. They would see our sun, but not as it is now. They would see it as it was during the last ice age on Earth, when mammoths roamed and humans were still hunter-gatherers. They would not see us. Our entire civilization, everything we've built, everything we've discovered, all of it exists in their future, in light that hasn't reached them yet.
This temporal disconnect means that, in a very real sense, we can never truly know the present state of the galactic center. We can only know its past. We can extrapolate, we can make predictions based on physics, but we cannot observe the black hole as it is right now, in this moment. And the black hole, for its part, cannot know us as we are now. If it had consciousness, if it could observe, it would only see us as we were in the distant past. There's something deeply strange about this. We share a galaxy with Sagittarius A. We orbit around it, in a broad sense. It holds our solar system in its gravitational influence, along with everything else in the galaxy. And yet we are separated from it not just by distance, but by time. We exist in different moments. We inhabit the same space, but different eras. We are connected by gravity, but separated by the finite speed of light. We are linked, but isolated, together, but alone. This is the nature of the universe we live in. Vast not just in space, but in time. Connected, but disconnected. Bound together by physical forces, but separated by the limitations those same forces impose. Nothing can travel faster than light, and so everything we see is delayed. Everything we know about distant objects is out of date. The universe we observe is not the universe as it is, but the universe as it was. A patchwork of different moments, different eras, all stitched together by the time it takes light to travel from there to here. And yet, knowing this, we can still understand. We can still make meaningful statements about reality, because the laws of physics are consistent, because black holes don't change quickly on human timescales, or even on the timescales of light travel across the galaxy. Sagittarius A today is almost certainly very similar to Sagittarius A 26,000 years ago. Its mass hasn't changed significantly. Its position hasn't changed. Its behavior is predictable based on the laws we understand. So even though we're seeing the past, we're learning about something that remains relevant to the present. The black hole's properties now are almost the same as they were then, and they will remain almost the same for millions of years into the future. Black holes are stable, enduring, slow to change. This makes them, paradoxically, easier to study, despite the temporal disconnect. We're not missing rapid evolution or dramatic changes. We're observing an object that has remained essentially constant over timescales much longer than the light travel time. Still, there's something philosophically intriguing about the situation. We study the past to understand the present. We infer the now from the then. We bridge vast gulfs of space and time using mathematics and physics and careful reasoning. And in doing so, we build up a picture of reality that is accurate and useful and meaningful, even if it's always slightly out of date. This is the human condition in a universe with a finite speed of light. We are always chasing information that has already happened. We are always looking at old photons, old data, old evidence. But we learn to compensate. We learn to extrapolate. We learn to understand the patterns and predict the future based on the past. And it works. It gives us real understanding, real knowledge, real power to predict and to comprehend. Sagittarius A is 26,000 years in our past, but it's also part of our present understanding. It's part of our current knowledge, part of the picture we have of the galaxy we inhabit. Time and space and knowledge become intertwined in ways that would have baffled our ancestors, but which we've learned to navigate. We've learned to think in terms of light travel time, to account for delays,
to translate between observed past and inferred present. It's become second nature to astronomers, this juggling of space and time, this eternal looking backward to understand the now. And all of this elaborate conceptual machinery helps us understand a simple fact. There is a supermassive black hole at the center of our galaxy. It's there now, it was there then, it will be there in the future. And we know this despite never seeing it directly, despite being separated from it by vast distances and vast stretches of time. We know it through the power of observation and reason and scientific method. And that knowledge is real as anything else we know about the universe.
Let's return for a moment to the question of what happens at the singularity. The singularity is the point at the very center of the black hole, where, according to general relativity, all the mass is concentrated. It's a point of infinite density, zero volume. All the mass of the black hole, those 4 million solar masses in the case of Sagittarius A, compressed to a mathematical point. Infinity divided by zero. The equations break down. They produce results that don't make physical sense.
This tells us something important. It tells us that general relativity, for all its success, for all its incredible accuracy in describing gravity and space-time, is incomplete. It's not the final theory. It's an approximation that works extraordinarily well in most circumstances, but breaks down in the most extreme conditions. At the singularity, we need something more. We need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. We don't have that theory yet. It's one of the great unsolved problems in fundamental physics. String theory offers one approach. Loop quantum gravity offers another. There are other proposals as well, but none of them are complete. None of them have been confirmed by experiment. We're still searching for the right way to think about space-time at the smallest scales, where quantum effects become important. And black holes are the places where this matters most. At the singularity, the curvature of space-time becomes infinite according to general relativity. But quantum mechanics suggests that space and time themselves might have a granular structure at the smallest scales. Perhaps space-time is not infinitely divisible. Perhaps there's a smallest possible length, the Planck length, about 10 to the power of negative 35 meters. If so, then the singularity might not be a true point. It might be a tiny region, incredibly small, but not infinitely small, where quantum effects smooth out the infinite curvature that general relativity predicts. This is speculative, of course. We don't know what really happens at the singularity. We can't observe it. Not only is it hidden behind the event horizon, it's hidden behind our own ignorance. Our theories fail there. Our mathematics breaks down. We've reached the edge of current human understanding. Beyond this point, there be dragons, or quantum foam, or something we haven't even imagined yet. But that's exciting, not discouraging. It means there's still fundamental physics to discover, still deep truths about the nature of reality waiting to be revealed. The singularity is a signpost pointing toward unknown territory, a reminder that we don't have all the answers yet, that there are mysteries still waiting to be solved. And every black hole, Sagittarius A included, is a natural laboratory for exploring these mysteries, a place where the quantum and the gravitational meet, where the very small and the very large become inseparable, where our theories are pushed to their limits and beyond. We can't reach the singularity, we can't observe it directly, but we can study the black hole's behavior, we can measure its properties, we can look for subtle quantum effects in the radiation emitted near the event horizon. We can test predictions made by different theories of quantum gravity. Sagittarius A, because it's so close and so well studied, is one of our best opportunities for this kind of work. As our instruments improve, as our theories become more sophisticated, we may be able to detect effects that reveal something about the quantum nature of space-time. Something about what really happens at the singularity. Something about how to reconcile gravity and quantum mechanics into a single unified theory. That work is ongoing. That quest continues.
And the black hole at the center of our galaxy is a key part of it. Not just an object to catalog and describe, but a window into the deepest mysteries of physics. A tool for exploring the fundamental nature of reality itself.
We're nearing the end now. The end of this journey. The end of this exploration. But before we close, let's think about what all of this means. What does it mean to live in a universe where such objects exist? Where the fabric of reality can be warped so severely that it creates one-way passages from which nothing returns? Where gravity can become so intense that time itself behaves differently? Where the most important structures are often invisible?
It means we live in a universe that is strange, profoundly strange. A universe that violates our everyday intuitions about how things should work. A universe where the rules operating at cosmic scales are very different from the rules we experience in our daily lives. And yet, these cosmic rules are discoverable, comprehensible, written in the language of mathematics. We can understand them even if we can't directly experience them.
It means we live in a universe that is knowable but not obvious, that rewards patience and careful thought, that reveals its secrets slowly to those willing to observe and measure and calculate, that doesn't hand us understanding on a silver platter, but makes us work for it, struggle for it, earn it through decades of dedicated effort. It means we live in a universe that is both humbling and inspiring. Humbling because it's so vast and we are so small, because the forces at work on cosmic scales dwarf anything we experience personally, because our entire species, our entire planet, our entire civilization is just a tiny speck in a galaxy that is itself just one of hundreds of billions of galaxies. But inspiring because despite our smallness, we can understand. We can figure things out. We can discover truths about the universe that were hidden for billions of years. We can make the invisible known. And it means we live in a universe that is ongoing, still evolving, still changing, still full of mysteries. The discovery of Sagittarius A is not an ending, it's a beginning, a foundation for future work, a stepping stone to deeper understanding. There are still questions to answer, still observations to make, still theories to develop and test. What is the nature of the singularity? How did supermassive black holes form? What role do they play in galaxy evolution? What happens to information that falls past the event horizon? Can anything ever truly escape from a black hole, even through quantum effects? These are questions for future generations, questions that will require new technologies, new mathematics, new ways of thinking about space and time and gravity. But they're worth asking, because the universe doesn't reveal its secrets easily. It requires persistence. It requires curiosity. It requires a willingness to look beyond what's obvious, to search for what's hidden, to believe in things we cannot directly see. And if we've learned anything from the discovery of Sagittarius A, it's that the most important things are often the hardest to find. The black hole at the center of our galaxy is a monument to that principle. It's been there all along, holding everything together, shaping the structure of the Milky Way, playing a crucial role in the cosmic story that led to us. And for billions of years, no one knew. For the entire history of life on Earth, for the entire evolution of humanity, for all of recorded history and most of unrecorded history, it was hidden, unknown, a giant waiting to be discovered. And then, in just the last few decades, we found it. We proved it exists. We measured its mass and tracked the stars around it, and built up a complete picture of what's happening at the galactic center. That's extraordinary. That's powerful. That's cause for celebration. We found the hidden heart of the galaxy, and in doing so, we learned something profound about our cosmic home, about the forces that shape it, about our place within it, about the nature of reality itself. Before we close, let's think more deeply about what it means that we live in an era when such discoveries are possible. For most of human history, the stars were simply lights in the sky.
Beautiful, mysterious, inspiring, yes, but fundamentally unknowable. Our ancestors could observe the patterns. They could track the movements of planets. They could predict eclipses and seasons, but they couldn't know what the stars really were. They couldn't measure their distances or their masses or their compositions. They couldn't know about black holes or galaxies or the vast scales of the cosmos. That changed gradually over centuries. First came the telescope, extending our vision beyond what our eyes could see. Then came spectroscopy, allowing us to analyze the light from distant objects and determine what they were made of. Then came photography, letting us capture and study images over long periods. Then came radio astronomy, X-ray astronomy, infrared astronomy, all the different windows into the cosmos that we've opened by detecting different wavelengths of electromagnetic radiation. And more recently, gravitational wave astronomy, giving us an entirely new sense, a new way of perceiving the universe that doesn't rely on light at all. Each of these advances expanded what we could know. Each opened new territories for exploration. Each revealed aspects of reality that had been hidden from all previous generations. And the discovery of Sagittarius A was made possible by this long chain of technological and conceptual advances. Without infrared telescopes that could see through the dust, we couldn't have observed the stars at the galactic center. Without adaptive optics to compensate for atmospheric blurring, we couldn't have achieved the resolution necessary to track individual stars. Without computers to analyze decades of data and calculate orbital parameters, we couldn't have proven the black hole's existence. Without Einstein's general relativity to provide the theoretical framework, we wouldn't have known what we were looking at. Science builds on itself. Each generation stands on the shoulders of previous generations. Each discovery enables future discoveries. Each tool we develop opens up new questions we couldn't have asked before. This is a cumulative process, a collective human endeavor that spans centuries and involves millions of people, most of whose names we'll never know. The scientists, yes, but also the engineers who built the instruments, the technicians who maintained the telescopes, the administrators who secured funding, the teachers who educated the next generation, the curious public whose support and interest kept the enterprise going.
And now we live in this moment, this brief window of time when we can look back and say, yes, we found it. We discovered the supermassive black hole at the heart of our galaxy. We proved it exists. We measured it. We understand it. That's our generation's contribution to the long story of human knowledge. And future generations will build on what we've learned, asking new questions, making new discoveries, pushing understanding even further. What will they discover? What will the astronomers of the 22nd century know that we don't? What will the physics of 300 years from now reveal about the nature of singularities, about quantum gravity, about the deep structure of space-time? We can't know. We can only lay the groundwork, provide the foundation, pass on what we've learned, and trust that those who come after will continue the work. That's a kind of immortality. Not personal immortality, but the immortality of knowledge. The understanding we build becomes part of the permanent record of human achievement. Long after we're gone as individuals, the knowledge remains. The discovery persists. Future students will learn about Sagittarius A, the way we learned about the moons of Jupiter or the rings of Saturn. It will become common knowledge, obvious, almost mundane. But it wasn't always obvious. It had to be discovered, proven, understood. And that work, that effort, that achievement will echo through time. Let's also consider the broader context of supermassive black holes in the universe. Sagittarius A is not unique. It's one example of a common phenomenon. Most large galaxies, possibly all large galaxies, have supermassive black holes at their centers. We've found them in galaxy after galaxy. The Andromeda Galaxy, our nearest large neighbor, has a supermassive black hole at its center too, even more massive than Sagittarius A. The giant elliptical galaxy Messier 87 has a black hole about 6.5 billion times the mass of the Sun.
That's more than 1,000 times more massive than ours.
This suggests that supermassive black holes are a fundamental feature of galaxy formation and evolution. They're not anomalies or rare exceptions, they're part of the standard structure of galaxies. And there's a surprisingly tight relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the mass of its central bulge. Galaxies with bigger bulges have more massive black holes. The correlation is remarkably precise. It suggests a deep connection between the growth of galaxies and the growth of their central black holes. This is still an active area of research. We don't fully understand the cause of this relationship. Did the black holes form first, seeding the growth of galaxies around them? Did galaxies form first, with black holes growing in their centers later? Or did both grow together in some complex feedback process where the black hole's energy output affects star formation in the galaxy, which in turn affects how much material falls into the black hole?
Evidence suggests it's the latter, that galaxies and their central black holes co-evolve through feedback processes. When a black hole is actively feeding, the energy it releases can heat gas in the galaxy, preventing it from cooling and collapsing into new stars. This regulates star formation. It prevents the galaxy from using up all its gas too quickly. And it explains why the most massive galaxies, which you might expect to have the most star formation, are actually quite dead. They've used up their gas, or rather, their central black holes have heated it to the point where it can't form stars anymore.
Sagittarius A fits into this broader picture. It's a typical supermassive black hole in a typical spiral galaxy. Not the most massive, not the most active, just average in the cosmic sense. And that makes it valuable. By studying our own galactic center in great detail, we learn about processes that operate in galaxies throughout the universe. The specific becomes universal. The nearby becomes a template for understanding the distant. And as we continue to observe Sagittarius A, as our techniques improve and our instruments become more sensitive, we'll learn more. We'll measure the black hole's spin, which tells us about its history. A rapidly spinning black hole likely grew through a steady accretion of gas from one direction. A slowly spinning black hole might have grown through chaotic mergers with other black holes. We'll detect gravitational waves from matter falling in, giving us real-time information about accretion processes. We'll observe relativistic effects near the event horizon, testing general relativity in extreme conditions. The work is far from over. The discovery of Sagittarius A was a beginning, not an end. It opened up a field of study that will keep astronomers busy for generations. And each new observation, each new measurement, each new insight adds to our understanding not just of this particular black hole, but of black holes in general, of galaxies in general, of the universe in general.
This is how science progresses, from the specific to the general, from careful observation to broad understanding, from questions to answers to new questions. The cycle continues, and Sagittarius A, our local supermassive black hole, is a key part of that ongoing cycle.
There's also something to be said about the technology that made this discovery possible. The telescopes used to track stars at the galactic center are marvels of engineering. The Keck Observatory in Hawaii, which Andrea Gez's team used, consists of two 10-meter telescopes. Each mirror is actually made up of 36 hexagonal segments that work together as a single surface. These segments must be aligned to within a fraction of a wavelength of light, and the alignment must be maintained even as the telescope moves and as temperature changes throughout the night. It's an extraordinary technical achievement. The adaptive optics systems are even more impressive. They work by measuring atmospheric distortion in real time using a guide star, either a natural bright star or an artificial star created by shining a laser into the upper atmosphere. The measurements are fed to a deformable mirror that changes its shape hundreds or thousands of times per second to compensate for the atmospheric turbulence. This effectively removes the twinkling, the blurring, the distortion that the atmosphere introduces. It allows ground-based telescopes to achieve resolution approaching what would be possible from space. Without this technology, the discovery of Sagittarius A would have been impossible from the ground. The stars at the galactic center are too close together, too faint, too obscured by dust. Even the Hubble Space Telescope, above the atmosphere, couldn't have done the job as well because it's optimized for visible light, and the galactic center is hidden in visible wavelengths. You need infrared, you need adaptive optics, you need large apertures to collect enough light, you need stable pointing to track the same stars over years and decades. All of these requirements came together in the instruments used by Genzel's and Gez's teams. And behind the instruments are people. Engineers who designed and built them, technicians who maintain them, observers who spend cold nights at the telescope, often just to calibrate the system or observe standard stars. Software developers who write the programs to analyze the data, graduate students who do much of the actual work, postdocs who bridge the gap between student and professor, senior scientists who guide the research and secure funding and mentor the next generation. Science is often portrayed as a solitary endeavor, the lone genius working in isolation. But that's rarely how it actually works. Modern science, especially observational astronomy, is deeply collaborative. It requires teams of people with different skills working toward common goals. It requires sharing data and techniques. It requires building on each other's work. The discovery of Sagittarius A involved hundreds of people over multiple decades. It was a collective achievement, and it stands as a testament to what humans can accomplish when we work together toward understanding. Let's return once more to the philosophical implications. What does it mean that the center of our galaxy is a black hole? What does it tell us about the nature of existence, about order and chaos, about light and darkness? On one level, it's simply a fact, a piece of information about the universe. The Milky Way has a supermassive black hole at its center. Okay, noted. Moving on. But on another level, it's profound. It challenges our intuitions about centers. We tend to think of centers as special places, sacred places, places of light and activity and importance. The center of a city has the tallest buildings, the most activity. The center of attention is where things happen. The center of a circle is a point you can locate, a place you can go to. But the center of our galaxy is different. It's a place you can't go to, at least not if you want to come back. It's not a beacon, but a trap. Not a source of light, but a sink for light. The organizing principle of the galaxy is not illumination, but gravitation. Not radiation, but consumption. The center doesn't shine outward, it pulls inward. And yet it's no less important for that. Perhaps more important, because without that gravitational pull, without that central mass, the galaxy would fly apart, structure would dissolve, order would become chaos. So perhaps we need to revise our metaphors. Perhaps centers don't need to shine. Perhaps the most important organizing principles work quietly, invisibly, in the background. Perhaps what holds things together is not always obvious, not always visible, not always what we expect. This applies beyond astronomy. In ecosystems, the most important species are often not the most visible. Keystone species can be small, obscure, easily overlooked. But remove them and the entire system collapses. In societies, the most important work is often done behind the scenes. Infrastructure, logistics, maintenance, all the unglamorous tasks that keep things running. In our own bodies, most of what keeps us alive happens below the level of consciousness. Our hearts beat without us thinking about it. Our immune systems fight infections without us knowing. The vast majority of biological processes that sustain life are invisible to our conscious minds. Maybe Sagittarius A is teaching us something about this principle. That the most important things are often hidden. That power doesn't always announce itself. That the forces that truly matter work quietly, consistently, without fanfare. The black hole has been there for billions of years, holding the galaxy together. And for most of that time, nothing knew it was there. It didn't need acknowledgement. It didn't need to be seen or understood. It simply did its job, exerting gravity, organizing matter, maintaining structure. And now we know about it. We've discovered it. We've brought it into the light of human understanding. But it hasn't changed. It's the same as it always was. Our knowledge of it doesn't alter it. Our understanding doesn't affect it. It continues as before, indifferent to our awareness. The universe doesn't need us to understand it. It works fine without our comprehension. But we need to understand, for our own sake, for our own sense of meaning and place, for the satisfaction of knowing what's real and true about the world we inhabit. That's the human drive, the need to understand, the refusal to accept ignorance when knowledge is possible, the insistence on asking questions even when the answers are difficult to find. And Sagittarius A represents the triumph of that drive. We looked at a place we couldn't see, inferred the presence of something invisible, and proved it exists. We brought hidden reality into the realm of knowledge, and in doing so, we changed ourselves. We expanded our understanding. We became more aware of the universe we're part of.
So here we are, at the end of our journey. We've traveled from Earth to the galactic center and back again. We've explored the nature of black holes and the structure of the Milky Way. We've contemplated mysteries and understood realities. We've thought about what's visible and what's hidden, about time and space, about humanity's place in the cosmos. And through all of this, one presence has remained constant: Sagittarius A, the supermassive black hole at the heart of our galaxy.
It's there right now, as you hear these words, 26,000 light-years away, though the photons carrying information about its current state won't reach us for 26,000 years. It's there, massive and invisible, pulling on everything around it with relentless gravity. Stars are orbiting it right now, whipping around at thousands of kilometers per second, tracing out their elliptical paths in the darkness. Gas is slowly spiraling inward, heating up, occasionally producing brief flares of radiation. The event horizon stands as an impassable boundary, a one-way door in the fabric of reality. And at the very center, the singularity waits, if it exists at all, a point where our understanding breaks down and mystery begins. All of this is happening right now, and it will continue happening tomorrow, and the next day, and for billions of years to come. The black hole is patient, eternal for all practical purposes. It will outlast the sun, outlast Earth, outlast humanity, if humanity has an end. It will be there when the Milky Way merges with Andromeda 3 or 4 billion years from now. It will merge with Andromeda's own supermassive black hole, creating an even larger black hole in the center of the merged galaxy. And it will continue, growing slowly, occasionally feeding, mostly dormant, for time frames that make the current age of the universe seem brief. We, on the other hand, are temporary. Our lives are measured in decades. Our civilization is measured in millennia. Our species might last millions of years if we're lucky, but even that is nothing compared to the lifetime of a black hole. We are brief flickers of consciousness in a universe of deep time. We are here for a moment, we observe, we understand, and then we're gone. But the understanding remains. That's what makes it worthwhile. That's what gives meaning to our brief existence. We live in a time when such understanding is possible, a time when we have the tools and techniques to peer into the galactic center and discover what's hiding there. A time when we can measure the invisible and map the unknowable and bring hidden truths into the light of knowledge. Not all times in human history have been like this. For most of our existence as a species, such knowledge was impossible. And in the far future, if civilization ever falls, it might become impossible again. But now, in this moment, in this era, we can know. And we do know. And that knowledge is precious. Think about what we've accomplished. We live on a planet orbiting an ordinary star in the outer reaches of a spiral galaxy. We're made of atoms forged in stutter furnaces billions of years ago. where biological organisms evolved to survive in a narrow range of temperature and pressure and radiation. We're limited by our senses, which detect only a tiny fraction of the electromagnetic spectrum. We're limited by our lifespans, which give us only a few decades to learn and discover and understand. We're limited by our location, stuck on one planet with no easy way to reach even the nearest stars. And yet, despite all these limitations, we've managed to discover a supermassive black hole at the center of our galaxy. We've measured its mass to within a few percent. We've mapped the orbits of stars around it. We've imaged the shadow of its event horizon. We've tested Einstein's general relativity in one of the most extreme gravitational environments accessible to us. We've added to the sum of human knowledge in a fundamental way. We've answered a question that previous generations couldn't even ask.
That's extraordinary. That's worth marveling at. Not in a self-congratulatory way, but in genuine appreciation for what collective human effort can achieve. We are capable of so much more than our individual limitations would suggest. Working together, building on each other's discoveries, we can understand things far beyond our immediate experience. We can reach across cosmic distances with our instruments and our mathematics. We can grasp truths about reality that seem, at first glance, impossibly remote.
Sagittarius A is proof of that, evidence of human capability, a demonstration that there are no questions too big to ask, no mysteries too deep to probe, no truths too well hidden to eventually reveal. We just need patience, persistence, curiosity, and a willingness to look beyond the obvious, to question our assumptions, to follow the evidence wherever it leads. As we close, let's think one more time about the night sky, about that band of light stretching overhead on clear, dark nights. The Milky Way, our home, our galaxy. 100 billion stars bound together by gravity, organized into a spiral structure, rotating slowly around a common center. It's beautiful to look at, inspiring, humbling. It's been a source of wonder for every human who has ever lived beneath it. Every culture has stories about it, myths and legends, trying to explain that mysterious band of light.
Now we know what it is. We know we're looking at our galaxy from the inside, seeing the combined light of billions of stars too far away to resolve individually. We know the Milky Way is a spiral galaxy, about 100,000 light-years in diameter, containing somewhere between 1 and 400 billion stars, along with vast amounts of gas and dust and dark matter. We know it's part of the local group of galaxies, which also includes Andromeda and several dozen smaller galaxies. We know it's moving through space at hundreds of kilometers per second, carried along by the expansion of the universe and the gravitational pull of nearby galaxy clusters.
And we know now that at its center, hidden behind curtains of dust, invisible to our eyes but detectable with our instruments, there is a supermassive black hole. 4 million solar masses of concentrated space-time, an object so massive and so dense that it warps reality around it, an event horizon from which nothing can escape, a singularity where physics as we understand it breaks down.
That knowledge doesn't diminish the beauty of the Milky Way. If anything, it enhances it. Because now when you look up, you're not just seeing light, you're seeing structure, organization, history. You're seeing the combined effect of billions of years of stellar evolution and galactic dynamics. You're seeing the result of gravity pulling on matter, black holes organizing galaxies, stars forming and dying and enriching the interstellar medium. You're seeing your cosmic heritage, the environment that made you possible, the galaxy that is, in a very real sense, your ancestral home. Every atom in your body came from this galaxy. Every thought you've ever had occurred in a brain made of atoms synthesized in stars and scattered through the Milky Way. You are not separate from the galaxy. You are made of it. You are a way for the galaxy to become aware of itself, to observe itself, to understand itself. When you look up at the Milky Way is looking at itself through your eyes. consciousness emerging from matter, awareness arising from cosmic processes, the universe experiencing its own existence through creatures evolved on tiny planets orbiting ordinary stars. And somewhere in that galaxy, at its very center, there's a black hole. Your black hole. Our black hole. The supermassive black hole that has been organizing and shaping our cosmic home for billions of years. It's been there all along. And now you know about it. Now you understand, at least partially, what it is and what it does. That knowledge connects you to it, makes you aware of forces and structures operating on scales far beyond your immediate perception, but nonetheless real and important. The next time you see the Milky Way, remember Sagittarius A. Remember the invisible giant. Remember that at the center of all that beauty, hidden in darkness, there's something strange and powerful and fundamental. Something that challenges our intuitions about reality. Something that required decades of patient work to discover and understand. Something that represents both the mystery of the universe and our ability to comprehend it. And let that fill you with wonder, with awe, with appreciation for the cosmos you're part of, with gratitude for being alive in an era when such knowledge is possible, with excitement about what else we might discover, with curiosity about what mysteries still remain, with humility about how small we are, and with pride about what we're capable of understanding despite that smallness. The giant has been found. The mystery has been unveiled. The hidden heart of the galaxy is hidden no longer. But the universe is vast, and there are more mysteries waiting, more giants to discover, more truths to reveal, more questions to ask and answer. The journey continues. It always continues, because that's what we do. That's who we are. Curious creatures on a small planet, looking up at the sky and wondering what's really out there, asking questions, seeking answers, building knowledge, understanding reality one discovery at a time. Sagittarius A is one discovery, one answer, one piece of the cosmic puzzle. But it's an important piece, a fundamental piece, a piece that tells us something profound about our place in the universe. We live in a galaxy with a supermassive black hole at its center, and now we know that. Now we can live with that knowledge. Let it inform how we see ourselves and our world and our cosmos. Welcome to the Milky Way. Welcome to your home. Welcome to a galaxy held together by an invisible giant. Welcome to a universe stranger and more beautiful than you ever imagined. The black hole is there, waiting, patient, eternal. And we are here, brief but aware, temporary but understanding, small but capable of grasping something vast. That's the human condition. That's our gift and our curse. To be conscious in a universe of such scale and strangeness. To be aware of our insignificance and our importance simultaneously. To be both humbled and empowered by knowledge. To live with mystery and understanding side by side, knowing that some questions have answers, while others remain forever open. Sagittarius A embodies all of this. It's known and unknown, understood and mysterious, visible in its effects but invisible in itself, real but unimaginable, part of our galaxy but alien to our experience. It's everything that makes the universe fascinating, everything that makes science worthwhile, everything that justifies the effort of looking up and wondering and asking and discovering. The journey we've taken tonight, from Earth to the galactic center, from ignorance to understanding, from mystery to knowledge, is the same journey that science has been taking for centuries, the same journey that humanity takes every time we push back the boundaries of the unknown. And it's a journey that never ends, because there's always more to discover, always deeper to go, always further to reach. But for tonight, for this moment, we've reached our destination. We've found the hidden giant. We've understood the invisible force. We've grasped something true about the cosmic structure that sustains us, And that's enough. That's more than enough. That's a gift to carry with us as we return to our everyday lives, as we go back to being small creatures on a small planet, as we resume our brief existence in the shadow of vast cosmic forces. But we'll carry with us the knowledge, the awareness, the understanding. We'll know that somewhere out there, at the center of the galaxy, Sagittarius A waits. 4 million solar masses of pure gravitational potential. A sleeping giant, a hidden heart, a darkness that holds everything together. And we'll know that we live in a universe capable of producing such objects, a universe governed by laws we can understand, a universe that is knowable, even in its strangest and most extreme manifestations.
That knowledge is a light in the darkness, not the light of stars or galaxies or any physical radiation, but the light of understanding, the light of consciousness, the light of awareness. We've taken something hidden and made it known. We've illuminated a corner of reality that was dark for billions of years. And that light, once lit, cannot be extinguished. It becomes part of the permanent record of human achievement, part of what we know, part of who we are.
So thank you for joining this journey. Thank you for taking the time to understand. Thank you for caring about what lies at the center of our galaxy. Thank you for being one of the humans who knows, who understands, who carries this knowledge forward. You are now part of the story, part of the collective human effort to comprehend the cosmos. And that matters. Your awareness matters. Your understanding matters. Because knowledge only has value when it's shared, when it's passed on, when it becomes part of the common heritage of our species. The black hole doesn't need you to know about it, but you are richer for knowing. Your life is deeper for understanding. Your perspective is broader for grasping your place in a galaxy with such a center. And maybe, just maybe, you'll share that understanding with someone else. You'll point up at the Milky Way and say, "There's a supermassive black hole at the center of that." You'll spark curiosity in someone else. You'll pass on the wonder, and the chain of knowledge will continue. That's how civilization works. That's how progress happens. Not through isolated individuals, but through communities of understanding, through sharing and teaching and learning together, through each generation building on what the previous generation discovered, through the slow, steady accumulation of knowledge that, over time, transforms how we see reality. Sagittarius A is part of that transformation, part of the shift from seeing the galaxy as a simple collection of stars to understanding it as a complex, organized system with structure and dynamics and a massive black hole at its center. We've moved from ignorance to knowledge, from mystery to understanding, and we've done it together as a species, through the collective effort of thousands of people over decades of work. That's worth celebrating. That's worth honoring. That's worth remembering. We found the giant. We solved the mystery. We illuminated the darkness. And now, as we close, as we end this journey, we can return to our lives knowing that we understand something profound about our cosmic home, something true, something real, something that will remain true long after we're gone.
The galaxy turns, the stars wheel overhead, and at the center of everything, in silence deeper than silence, in darkness more complete than any darkness we can imagine, Sagittarius A waits, patient, ancient, eternal, the sleeping giant, the hidden heart, the gravitational anchor of our galaxy.
It's there. It's real. It's been there all along. And now, finally, we know. Welcome to Infinite Science. Thank you for journeying with us tonight into the hidden heart of the Milky Way. Keep looking up, keep wondering, keep asking questions. The universe has more secrets to reveal, more mysteries to illuminate, more giants to find. And we'll be here, exploring them together, one discovery at a time. The night sky awaits. The cosmos calls.
And somewhere in the darkness, invisible but known, the giant watches over our galaxy.
Good night, and may you never look at the Milky Way the same way again. We've traveled from Earth to the galactic center and back again. We've explored the nature of black holes and the structure of the Milky Way. We've contemplated the scale of cosmic forces and the process of scientific discovery. We've thought about visibility and invisibility, time and space, knowledge and mystery.
And through it all, one truth remains. Sagittarius A is there, at the center of our galaxy, 4 million times the mass of the Sun. Invisible but real, silent but powerful, a sleeping giant that holds everything together. It was there before we knew about it. It will be there long after we're gone. It doesn't care whether we understand it or not. It simply exists, exerting its gravitational influence, maintaining the structure of the galaxy, fulfilling its role in the cosmic order.
But we do understand it now, at least partially. We know it's there. We know its mass, its size, its location. We know how it affects nearby stars. We've seen the shadow of its event horizon in radio images. We've measured the orbits of stars around it with exquisite precision. We've proven, beyond reasonable doubt, that a supermassive black hole sits at the heart of the Milky Way.
That knowledge, hard-won and carefully verified, is now part of human understanding, part of our collective story, part of what we know about the universe we inhabit. And maybe, just maybe, that knowledge changes something. Not in a grand, dramatic way, not in a way that affects our daily lives directly, but in a subtle way, a deep way, a way that expands our awareness and deepens our appreciation for the cosmos.
The next time you look up at the Milky Way, if you're lucky enough to see it on a clear night far from city lights, you can know that there's a giant hiding there, a massive, invisible presence at the galactic center, a black hole that has shaped the structure of our cosmic home and made our existence possible. You won't be able to see it. No human ever will, not directly, but you'll know it's there.
And that knowledge, that understanding, connects you to something vast and ancient and ongoing, connects you to the galaxy itself, to billions of years of cosmic history, to forces beyond normal comprehension that nonetheless follow rules we can understand. That's the real gift of astronomy, of science, of patient, careful investigation of the natural world. Not just facts and figures and technical details, though those matter, but connection, perspective, context, a sense of our place in the larger whole.
We are small, but we're also capable of understanding things much larger than ourselves. We're temporary, but we're part of patterns that endure. We're limited, but we can transcend those limitations through tools and mathematics and collective effort. Sagittarius A reminds us of all of this. It's a challenge and an invitation, a mystery and a revelation, a darkness that illuminates, and it will always be there, waiting at the center of everything, holding our galaxy together with invisible hands, a testament to the strangeness and beauty of the universe we call home.
Welcome to the Milky Way. Welcome to your cosmic home. Welcome to a universe stranger and more beautiful than you ever imagined. The giant has been found. The mystery has been revealed. The hidden heart of the galaxy is hidden no longer. And the journey of discovery continues, always continues, because the universe is deep, and there's always more to learn, always more to discover, always further to explore.
The black hole sits at the center, waiting, patient, eternal. And we, brief sparks of consciousness in the cosmic darkness, continue our quest to understand, to know, to illuminate the shadows with the light of knowledge. That's the human story. That's our purpose. That's what makes us special. We found the giant, and in finding it, we found a piece of ourselves, a deeper understanding of our place in the cosmos,
a connection to forces and structures that dwarf us in scale, but are nonetheless part of our story. Sagittarius A, the black hole at the heart of the Milky Way. The invisible giant, the sleeping dragon, the hidden anchor of our galaxy. It's there, it's real, it's been there all along, and now, finally, we know. The galaxy turns, the stars drift slowly overhead, and at the center of everything, in silence deeper than silence, in darkness more complete than darkness, the giant waits. Patient as only cosmic forces can be patient. Ancient as only the universe can be ancient. Present as only gravity can be present.
It doesn't know we found it. It doesn't care that we understand it. It simply is. But we know, we understand. We've peered through the dust and the distance and discovered what lies at the heart of our cosmic home. And that knowledge, that understanding, changes everything. Welcome to Infinite Science. Thank you for journeying with us tonight. Keep looking up, keep wondering, keep asking questions. The universe has more secrets to reveal, more giants to find, more mysteries to illuminate. And we'll be here, exploring them together. Good night.